It's a pleasure to be here. So I want to acknowledge that some of the work I'll be talking about is with and by collaborators at AI2 who also provide some content for this talk. And this really dovetails nicely with what Tom was talking about. So I think there'll be some good synergy. I think Tom set this up really well, talking about GPT and NLP and how amazing these general purpose models are. So I won't dwell further on that. But I do want to make a point about why the impact is so large of creating these kinds of general purpose models. So if you came to me just 1 year ago and you said, I want to make a new model that'll do some custom NLP task, I would say, well, it's kind of a straightforward but arduous journey. First, you have to get an advanced degree, take specialized coursework in ML and NLP and other topics. Then you have to gather and annotate a lot of training data. Then you have to design and train a model and then deploy it to the cloud. And then you have something that can do your new custom NLP task. If you ask me today, how do you do this? I would say, well, go to chat.openai.com and type in what you want, and it will do that task for you. So the potential for impact of a technology is really the ratio of its utility and the cost to making it do that useful thing. So when you bring that cost down to near zero, it really explodes the potential impact of that technology. LLMs are still mainly limited to text. As Tom said, GPT-4 can take as input an image, but it's generating text. And so in this talk, I want to see how we could make systems that can not only process text, but can also see and generate images, can also hear and generate audio, and can also act. And we can only imagine if we had these capabilities, what range of new applications it would enable. So I'm going to talk about two ways of doing this. One of them through treating AI as a kind of general data processor, and one as a visual programmer. And then I'm going to talk about some of the limitations that AI still has and what I think we need to do to address them. So it's not going to be easy to create these kind of multimodal general purpose systems because there's big differences between language data and other kinds of data like vision data. Language is made to communicate. It's easy to encode, and it implies a lot with a little bit of data. For example, if your friend comes to you and says, I'm pregnant, it only takes 3 tokens to represent that information, but you know that those 3 tokens are going to change your friend's life. Vision, on the other hand, is observational. It's hard to encode, it takes a lot of data, and it doesn't imply very much. So here's a picture that I took in Paris a couple of weeks ago of a cone on top of a statue's head. It takes 1,000 tokens to represent this, and it's kind of an interesting picture, but it's not going to change anybody's life. Another big difference is in the output space. So it's very natural to think about NLP tasks as like a text-to-text processing, just like we can get a lot done merely through conversation where we're just exchanging language information. But often when we take an image as input, there are different kinds of things that we might want to output. For example, we might want to detect objects and produce boxes around them, or to label the pixels of the image, or to categorize the image, or to label key points for human pose estimation, or depth values, or generate a caption. So to get to how we can create these more multimodal general purpose systems, I want to take a step back and look through the evolution of how these abilities have started to develop over the last few years. So just a few years ago, we had only special purpose models where you would have an architecture and a model that's designed for some particular task on a particular data set, like doing visual question answering on Coco or some specific data set. Then we started to see multi-purpose models like Mask RCNN, where you have an encoder that is used to generate information about the image, and then you have different decoders off of that can do related tasks. For example, being able to segment out the object, being able to give the label of the object, and being able to assign key points to the object. Then we started using pre-trained backbones where you can train this encoder on a really large data set and then repurpose it for other specialized tasks by fine-tuning it for those tasks. And then these ideas can be combined to create multitask models where you have your pre-trained backbone, multiple specialized heads that can do different kinds of decoding tasks, and train all of them jointly using fine-tuning. So when my colleagues and I started to look into how can we create more like vision-based general purpose systems, the first question we asked was how can we create models that don't have these task-specific components? So what I mean by that is that traditionally when you created a vision system, even if it was this kind of multitask vision system, you'd have an image going in, you'd have some core network parameters that create an encoding of the image, and then you'd have a decoder not only for every different kind of task, but also for the data distribution that they're learning on. So you might have one for referring expressions, another one to produce captions on the COCO data set, another one to produce captions on the visual genome data set. And if you wanted to add more tasks, like VQA, you'd add a visual question answering, you'd add another decoder for that. If you wanted to add even the same kind of task, but on different classes or a different data set, you'd have to add another decoder. And so the problem is that you have a bunch of overly specialized models that are really restricted to a very specific task and domain. And if you want to do something that's kind of similar to those, but a little bit different, it doesn't really work. They don't apply to that slightly different kind of task or setting. And so the idea is that we instead want to think about the model not as solving a task, but as processing a modality. So you have, for example, an image that is encoded, text can be encoded, different spatial information about the image can be encoded, that gets processed, and then it outputs information that can then be decoded into these different modalities. The first version of this that we created was, we called it GPV for general purpose vision. And the idea was that you could take as input an image and a text instruction, and then the system would produce text and bounding boxes. So for example, if you said, put in this image on the left and said, what color is the dog? Then it would say brown and it would detect the dog. If you say, are there trees being seen? It would say yes, and then it would detect the trees. If you say, generate a description for the image, it would say a dog and a cat lying on the bed, and then it would detect each of them. And so what was interesting about this to us is that it's not only able to solve the specific tasks that we trained it on, but it could solve related tasks and tasks on other data distributions. So this was a way of moving from task-specific heads to modality heads, enabled supporting a range of tasks rather than a set of specific tasks. But there were some things unsatisfying about this system. I didn't really talk about it, but it's kind of complicated. We have all these specific architectures for vision, another specific architecture for language, ways of combining them. And so it wasn't clear to us, how are we going to scale this up to deal with more modalities and to deal with an even broader range of tasks? And so the next question is, can we treat all of these different modalities in a more unified way, instead of having specialized architectures for each of them? And so that led to a system called Unified I/O. The idea is that you can treat these different kinds of information, you can just turn them into data packets that can be mixed together. So you can encode different kinds of images, natural images or images of masks, as well as text, as a set of tokens, process them with a model that then outputs more tokens that can be decoded into different kinds of images and into text and other kinds of data like location data. And then this can solve a broad range of tasks. So for example, if we have an image like this cat under an umbrella and text, what is the color of the cat? There'll be some encoder for the text, a cent piece encoder, which is similar to what GPT uses, that then turns that text into a set of discrete tokens, just integers that represent the text. And likewise, you can take the image, break it up into patches, and represent those patches with integers in a different range. then put them into a transformer, which mixes and aggregates the information from all of these different tokens of data, and then outputs another discrete token sequence, integers of different ranges for text and images. So in this case, it could be decoded into brown. If you say segment the cat, you can process that segment the cat with the same encoder, but now the output should not be text, it should be an image. And so the system will output a discrete set of tokens that corresponds to image patches that can be interpreted by an image encoder decoder. And in this work, a pre-trained frozen encoder called VQVAE is used, and that's able to interpret these like integer patch representations into an image, in this case, a segmentation mask for the cat. And the same decoder can be used for other things, like producing pixel intensities that represent depth values. And the same language decoder can also be used to represent information that's not natural language, but corresponds to image locations or controls or something like that. Now, this system was trained on 60 million image text pairs, and it was trained similar to GPT on a kind of generative task, in this case, a task called denoising, where you're trying to fill in the missing blanks in either the images or the text. And then it was fine-tuned on a large number of tasks spanning 90 different data sets. And so it can do things like, you can blank out part of the image and then say, fill it in with a train, and it can do that. Or you can do a paint by color to generate this image of the elephants tussling with each other. Or you can ask geometric questions, like what are the surface orientations in this image, and it generates a normal map. You can also detect things like find the parking meter, or find the guy with a gray tie, or identify key points on objects. And you can generate language, like describe the image or describe some region in the image. And as well as these, you can also do pure natural language tests also. So here we have a single model that supports a variety of tasks for parsing and producing images and text. And then we wanted to see, can we take it further? Can we add video and audio and controls? And so that's work that we're currently doing, and we call it Unified I/O 2. So we can process images as well as a sequence of images so that we can process video clips. We represent audio as a spectrogram and can, again, process a series of those spectrograms, and can also input text. It's the same kind of architecture, more parameters. It's able to output text, location information, and action tokens that represent controls, as well as audio spectrograms that can be turned into WAV files and images of various sorts. It's trained on even more data, billions of examples, including 500 million image text pairs and 80 million video clips, and on a wide variety of tasks. And so now it can do things like describe the image with a brief description, an old wooden jetty, or with a more detailed description, the image captures a moment of serenity and tranquility amidst the vastness of nature. But you can also do things like edit the image. You can say, remove the dock, or imagine you're Van Gogh, now paint this image, or add an aurora to the image, or render a sunset. And we can generate audio, like generate music for this scene. And it generates a kind of like a pleasant, peaceful kind of music. Or make the image haunted, and then generate music for that scene. And it creates much more spooky music. And we can even do things like say, look at this image, now imagine how you would move in that image, take that step, and then generate what you would see, and keep doing that. And so the system's able to synthesize navigating through this environment based on that one image. So in this way, we're able to process text, image, audio, video, and more. But as you've noticed, you keep on, as these systems develop, you tend to be adding more parameters, more data, more compute, and as Tom said, it can cost tens of millions or even hundreds of millions of dollars to train these systems. So is there another way? One other way is through visual programming, which is related to something that Tom also mentioned in his first trend. And this is work by my former student, Tame Gupta, where you need little or no new data, little or no learning, and you're leveraging specialized models. So for example, if you want to tag the characters on the TV show Big Bang Theory, the way that you or I would do it is we'd find the faces, we'd look up who these people might be, find pictures of them so that we can match the faces to the names, and then annotate the image. To do that with something like Unified I/O, it's really complicated. It has to have all this background knowledge about the TV show. It needs to have all these vision capabilities, the ability to annotate, to know the different steps it should do, and then to do all of those steps all within some homogeneous system. On the other hand, writing a program to do this isn't super complicated. And so the idea of visual programming, which there's also versions of this that have been created for robotics and other areas, is that you have some language description of a task, you generate a program using an LLM, that program operates on the input that you provide it, and using a standard interpreter, and then solves the task. And these programs can call AI models like object detectors or segmenters or classifiers, as well as image manipulating functions, knowledge retrieval like GPT, and other simpler operations. And so with a few examples, it can learn to answer questions or to edit images, like putting sunglass face on Daniel Craig, or replacing the desert under the car with grass, or doing an image pop of Barack Obama. So what we had before are a bunch of specialized models that are like having different instruments that can each play a particular tune, but it's not clear how to get them all to work together to do the thing that you want. One approach to this is to do the one-man band, and that's like Unified I/O 2, where you have like one person that learns how to play all of these instruments together and make them all synchronized. So that's an approach, that's like GPV4V as well, but it takes a lot of training to do that. Another approach is visual programming, which is like the conductor. It can't do any of those tasks, it can't play any of those instruments, but it knows how to coordinate them to make a beautiful symphony. And I think in the end, it's a combination of these that we need. We need the ability to integrate various kinds of information, but we also need the ability to coordinate specialized processes so that we can solve more complex tasks. So I want to end just by mentioning a couple of open problems that I think are really important in terms of understanding the limitations in the future of AI. So what we really want are AI models that are capable of anytime learning. They can receive new data in any order, quickly use new information, and continuously improve. But what we have for the most part is batch training. You train for a long time, freeze the parameters, and deploy it. We want any form learning that can learn from examples, instruction, feedback, demonstration, but mainly we still are learning from examples. We want to be able to retain memories of episodes and interactions so that we can collaborate with AI agents. But mostly systems have a memoryless state where they don't remember what they processed yesterday. And the key, I think, is memory. Humans have fantastic, complicated, heterogeneous memory systems, including sensory memory, various kinds of short-term memory, an instance-based memory that is able to store new information without overwriting, a consolidated memory that integrates lots of information and generalizes, but slowly updates and is ever changing, and various other specialized memory systems. While AI basically, if you look at a transformer, it has a kind of working memory and a long-term implicit memory in terms of the MLPs and attention weights. And we know from human studies that if we lose our ability to form new long-term explicit memories, there's still lots of stuff we can do, but we lose really important capabilities to be a fully independent and highly contributing member of society. In the same way, if we want AI to have human-like ability to learn and collaborate, we need more comprehensive memory systems. So to conclude, GPT demonstrates the power of flexible AI models. We can bring that flexibility to other modalities through two paths. unified models that treat AI as general data processors, and using LLMs to plan and use tools which can include AI models. But if we want to be able to create systems that have a kind of human level intelligence and ability to collaborate, then we need better memory systems that are able to retain history, continually learn, and learn from more varied sources. Thank you.
Derek Hoiem.